Welcome to The Explainer. Today, we're taking a deep dive into a really critical, but honestly surprisingly overlooked bottleneck in AI model training. We're talking about data provenance. Think about it. When an AI ingests millions of documents, how do we actually track where every single piece of information came from? And even more importantly, what happens when we're legally required to remove some of it? It's a massive challenge, and today we're looking at a pretty fascinating new solution called OriginBlame.
So it all starts with this one fundamental question. How do you make an AI forget? On paper, sure, we have the math to do it. But in practice, well, there's a huge gap between our theoretical unlearning algorithms and the messy, complicated reality of AI training pipelines. We just simply lack precise records of exactly which training examples belong to which author once that data is fed into the machine. Okay, let's dive into our structured agenda for today. We'll start with Section 1, the AI unlearning problem. Then we'll move into Section 2, introducing OriginBlame. After that, Section 3 covers how OriginBlame works, followed by Section 4, measuring the impact. And finally, Section 5, developer integration steps.
All right, kicking things off with Section 1, the AI unlearning problem, compliance meets compute. So the crucial point here is understanding catastrophic over-deletion. Imagine you're an ML engineer, right? Someone legally requests the removal of their data under privacy law. Because you can't map their specific identity to individual records inside your trained model. You face this nightmare scenario. You are forced to use a pretty brutal standard workaround, which is deleting entire files or even massive monolithic data sets, just to make sure that one single author's data is gone. It wastes an immense amount of compute and honestly just destroys your model's efficiency.
And here is the real compliance bottleneck. We actually do have sophisticated unlearning algorithms out there. Things like negative preference optimization, or NPO, and representation misdirection for unlearning, usually called RMU. But here's the catch. They require a known forget set to actually work. Because our current data sets operate as these big monolithic blobs, we know exactly who we need to forget, but we have absolutely no idea which data to forget at a granular training level. This practical gap is essentially stalling real-world compliance from major regulations like the GDPR and the AI Act. Moving right along to Section 2, introducing OriginBlame Precision Data Provenance.
To solve this headache, researcher Holland Zhu introduced a total paradigm shift, and this brilliantly illustrates that shift. Traditional data version control tools, things like DVC, LakeFS, or Delta Lake, they all operate really broadly at the file or data set level. But OriginBlame, or OB for short, operates down at the record and token level. It completely changes the resolution of our data tracking, taking us from these broad, sweeping strokes to literal pinpoint accuracy. By operating at this granular level, OriginBlame tracks an author's identity all the way through those complex data processing pipelines. And crucially, this metadata actually survives data cleaning and tokenization. It's incredibly resilient. This allows the system to seamlessly resolve those tricky revocation requests using deterministic queries. So no fuzzy guessing involved whatsoever. It identifies the exact training examples to forget without forcing you to rewrite your training loops or hack apart core framework internals.
Which brings us to Section 3, how OriginBlame works, tracking identity through pipelines. Let's see how this builds step by step inside the architecture for just a single record. First, instead of treating datasets as big blobs, OriginBlame attaches provenance metadata to individual records right at ingestion. Second, it propagates that very specific identity through every single stage of your processing pipeline. Third, when a revocation request finally arrives, it runs deterministic queries. And fourth, it outputs the exact, precise forget set ready to be consumed by your existing unlearning algorithms. Let's jump to Section 4, measuring the impact, the benchmark data.
Now, what's really interesting about this slide is the massive reduction. Let's look at the hard numbers. They tested this on a huge data set of nearly 220,000 Wikipedia pages against a 1.7 billion parameter model. Traditional dataset level methods, they resulted in a catastrophic over-deletion ratio of 101:1. But with OriginBlame's record-level provenance, that ratio plummets all the way down to just 1.3. It virtually eliminates over-deletion, preserving your valuable compute and your data.
And check this out, 42%. Because the forget set is so incredibly precise, the unlearning effectiveness just skyrockets. Utilizing these provenance-based forget sets improved unlearning accuracy by an impressive 42% compared to a random baseline selection. So you're not just saving compute, you are getting vastly superior unlearning results. It's a real win-win.
Now, I know what you're thinking. Any developer is immediately going to ask, okay, but what does this cost me in performance? Well, the throughput overhead is remarkably minimal. Integrated into Hugging Face datasets, it adds just 1.3 to 4% overhead. For data trove, it's between 2.1 and 19%, which scales linearly with your pipeline's complexity. But here's the absolute best part. This cost is strictly confined to the data preparation stage. For inference-only deployments, OriginBlame adds absolutely zero runtime penalty. None. It's entirely viable for production pre-training and fine-tuning.
And our final part, Section 5, Developer Integration Steps, Implementing OriginBlame.
If you are managing training data pipelines right now, your integration basically comes down to 3 main steps. First, instrument your data loaders. Wrap your Hugging Face or data trove processing steps with Origin tracking hooks to make sure you attach that author metadata before tokenization happens. Second, pin your schemas in a queryable format. Store your author to record mappings in something like Parquet, partitioned by author IDs. Do not just embed this metadata in unstructured text, it won't work. And third, when a request comes in, query that index directly to generate your forget sets deterministically. You want to avoid fuzzy matching at all costs.
To finalize the whole unlearning process, you just take that precise deterministic forget set and feed it directly into your existing algorithms like NPO or RMU. But a quick word of warning regarding the architecture. Do not attempt live weight pruning during your training loop. It's also super important to profile your data loading stage before and after integration, just so you can baseline your throughput costs. And remember, OriginBlame solves the mapping problem. It does not magically replace your deduplication or quality filtering. You still have to combine it with your standard data curation workflows to get full coverage.
So we've seen how tracking data at the record and token level completely transforms the really messy process of unlearning into a highly precise, efficient operation. Which leaves us with this final, provocative thought to consider. With precise unlearning now computationally viable and highly accurate, how will systems like OriginBlame redefine real-world compliance for stringent frameworks like the GDPR and the AI Act? The bottleneck is clearing up, and the future of responsible AI training is looking much, much sharper. Thank you so much for joining me for this explainer, and as always, keep learning.